Hello everyone, welcome to the another session of digital signal processing. We have started discussing on multirate digital signal processing, and today we'll be discussing about new technique which is called as interpolation, and also we'll be discussing about polyphase filter structures. So in the last session we had discussed the introduction to multirate digital signal processing, what it is and how we carry out it or how do we implement it. So we had seen that there are two techniques of implementing this multirate digital signal processing. One is decimation, that we have already discussed in the previous session, and today we'll be talking about the interpolation. So in the decimation we have seen that whenever our desired sampling frequency is less than the sampling frequency of the signal we already have, we have to decrease the sampling frequency by, say, a factor m. So that can be any integer factor. I have to decrease it by 2, I can decrease it by 4. So that many number of samples from the given signal xn are removed. So actually we are losing certain part of information, but yes, that is not going to affect the quality of my signal that I am going to use for any kind of application. Similarly, for a given signal of frequency, say f, I need to increase the number of samples in a signal. I need a sampling frequency of say 48 kilohertz and I already have a signal of sampling frequency say 34 kilohertz. So to increase the number of the samples, this particular technique which is called as interpolation is implemented. So this process of increasing the sampling rate of a signal is called as interpolation, or I may also call it as sampling rate expansion. Sometimes I also call it as upsampler as well. So what do I see here mathematically? I'll be using this representation of L here, the way I was using the particular alphabet M in the decimation. So I'll be talking about this L, and this L is an integer number and the signal is xn. So what is happening here? The ratio T dash by T is 1 by L. So this T dash is the new sampling period which I desired, and T was the sampling time corresponding to the sampling rate at which this given signal xn has been obtained. So this particular ratio, that is T dash by T, is 1 by L, or in a simple way if I want to represent that, T dash is equal to T by L. So L is any integer number, that means the time distance between the signal which I have. If these are my signal sample and this is my duration between two samples, this duration is going to be decreased. I'm going to insert certain values here in between these two samples. So time period between two samples is decreased, and that factor of scaling is L, which can be any integer number. Same thing can be seen for the frequency as well. The new frequency f dash is reciprocal of the new time that we have obtained after this interpolation, or I can say that new frequency f dash has been increased by the factor L. So the discussion which goes for the time period, that we are decreasing the sampling time period, the distance between two samples. When we talk about the frequency, we are increasing the frequency of the given signal. So interpolation of the signal xn by the factor L refers to process of interpolating L minus 1 samples between each pair of the samples. We'll see this into the numerical, that whatever two samples have been given to me, between these two samples I am introducing L minus 1 sample. That means if I want to interpolate by a factor say 4, then I am interpolating 3 samples in between every pair of samples. So the signal that I obtain, I'll be representing it by any symbol, say it is Wm. I'm interpolating it by L minus 1 sample. So this new signal and the signal to which I am converting the sampling rate xm, they are related to each other as Wm is xm by L, where this m can be any integer number, and at all other values it would be 0. The same thing can be represented in a digital system by taking Z transform. So this Wm is the interpolated signal. This would be represented in the form of the definition of Z transform, that is Wm Z raised to the power minus m, and it is infinite summation. This can also be represented as, if this Z is evaluated onto a unit circle, then what I am doing, I am increasing the frequency. I am increasing the frequency by a value L. So this can be represented as Z raised to the power minus m multiplied by L after interpolation, or if I talk about in the form of omega, then I can represent it as omega L. So initially the frequency omega has now been converted to omega into L, again L being any integer number. Now, in this process of introducing number of samples in between given samples, what is happening, I would see into the spectrum, this Wm which I am obtaining. When I try to draw its spectrum, what do I see? That multiple copies of signal have been generated, and these multiple copies are called as images of the signal. So to remove these images from the output signal, I have to again use certain kind of technique, which is nothing but a simple filter. And this filter would have a spectrum, like it would have a gain of G, it can be any integer value as per requirement. The gain would lie in the frequency band minus pi by L to pi by L. So only frequency within this band would be amplified and all other frequency would be attenuated. So the concept of images that we are talking about, that multiple images of the signal is being created, they would be filtered out from the interpolated signal. So if I want to look at the spectra of overall signal which I am receiving at the output, that would be the multiplication of the filter transfer function and the input signal in the frequency domain. And this can also be represented as convolution of the transfer function of the filter which I am choosing and the input signal which has been interpolated by the value L. So let us see how this spectra goes around. First stage is interpolating the given signal xn with the value L, which is resulting into a new signal whose frequency has been increased by the factor L. And because this Wm has the problem of generating the images, or when I look at the spectrum of this Wn, I can see multiple copies of this signal at the higher frequency. I'll be using a filter, and after I have filtered out this Wm with this filter characteristics, I'm getting Ym, which is interpolated signal, and all the images have been removed from it. So looking at this diagram, this is the frequency spectrum of the given input signal. This is the spectrum of the interpolated signal. So I can see that this spectra is same, but it is compressed between the range 0 to pi by L. But same spectra is being repeated at the higher frequencies as well. So this is what we were talking about, generation of images when I interpolate my given signal. So these images would be removed with the help of this filter. So this is my output signal where all these images have been removed and I'm getting my interpolated signal. So I see that the signal remains the same, only the width of this frequency band has been scaled down by the factor L. So I'm not introducing any kind of the distortion into the envelope while I'm performing this process called interpolation. So this is the same, the spectrum of the upsampled signal. How does this obtain? If I want to show it like this particular in the time domain equation. So I know that whenever I'm obtaining this Ym through this filter is giving me the output, which is the convolution between input signal, which is Wn, and the filter transfer function, that is Hm. So I'll be representing this mathematically here, that the output of this particular system which I'm talking about, Wn, this is interpolated signal xn, and output Ym is the convolution between these two transfer functions. So this is the same thing which have been representing in different format, in the form of Z domain, in the form of e raised to the power j omega, and so on. So individually looking at the spectrum, this is spectrum corresponding to xn. This is spectrum corresponding to my filter HN, this is the output which I am obtaining and having images. And once I filter out this signal, this is my output. So I can see this is my input, initial stage, and this is my output after interpolation. And this filter which I am using here, because this is removing all these images, the values at the higher frequency, this is also called as anti-imaging filter. The way we have anti-aliasing filtered in decimator, that is important to remove the aliasing. Similarly, it is important to have an anti-imaging filter in the interpolator as well to get an undistorted output. So to look at here, that how do we numerically solve this interpolator? I want to obtain a two-fold expanded yn signal of the given signal xn, which is having value n for every value of n greater than 0. So how does this signal look like? The signal xn looks like n is equal to 0, the value is 0, n is equal to 1, the value is 1, for 2 it is 2, for 3 it is 3, and so on. I need to perform two-fold expansion. That means the L that I'm going to use here is 2. And as per the definition we have discussed, the process of interpolation is introducing L minus 1 zeros in between two samples. So if I talk about these two samples, which is x0 and x1, I would introduce a position here, a value 0 here. These are two samples, I'll introduce a 0 here, and so on. So if it is 2, 2 minus 1 is 1. So I have to introduce 1 0 between pair of two samples. So how the complete signal would look like? These are the interpolated zeros between every two samples. This is how we implement the interpolation. But actually these positions do not have the value 0. We have to approximate these value by predicting this previous sample and the next sample. It would certainly have certain value which would help me in generating or reconstructing the signal. Next is, if I want to convert this particular conversion of sampling rate where the number is not now integer, rather this is a rational factor. So till now we were talking about m, which was integer, we were talking about L, which was integer, but now we'll be talking about a factor which is a ratio of m by L. So what do I see here? The time period which is going to change would also change as a rational factor. The frequency which is going to be increased or decreased, it would be increased or decreased by a rational factor. This is also called as resampling, or the structure that I'm going to use here would be called as a resampler structure. So it is a combination of both, where I want to decimate it by factor m, I'll be using a decimator. Where I'll be using, or I want to implement this scaling by L, I'll be implementing one interpolator. So nothing new has emerged here with this rational factor upsampling or downsampling or resampling. We are using the two basic techniques, decimation and interpolation, that we have discussed one by one. But one thing which I have to remember, whenever I am performing this resampling, and I am performing this resampling using decimator and interpolator, the position of these two processes cannot be arbitrary. It has to be like this. First we have to interpolate that particular signal, and then we have to decimate it. That means whenever I am decimating, that means I am losing the information. So before I am losing certain amount of information, I have to interpolate that signal so that reconstruction of signal is proper. So here this is upsampler, this is my anti-imaging filter, this is my anti-aliasing filter, and this is my downsampler. So the entire process would be the replica of decimation and interpolation, but interpolation would precede the decimation process. These two filters that we were talking about separately as anti-imaging filter and anti-aliasing filter, either I can design them as independent filters, or I can design a common filter which is fulfilling the requirement of both the processes. So this filter can have a characteristics like this would give me a gain of L in a band of frequency which is says minimum of pi by L or pi by M. So if pi by L is minimum, this gain would be for the frequency in the range minus pi by L to pi by L. If pi by M is minimum, then I would choose this process to range from minus pi by M to pi by M. So in this way, I can obtain the resampling by a rational factor. Talking about different structures for FIR, if we introduce these decimator and interpolator, what is going to happen? This HN would have a filter structure, which would be any kind of filter that we have already discussed. This is a direct form structure. So nothing is going to change with interpolator and decimator. The form of structures which are applicable for FIR filter structure would be applicable here, with only one change, that when I'm talking about decimator, this decimator would be placed after HN. And similarly, when we're talking about the interpolator, this process of interpolator, that is upgrading by the value L, would be preceding this FIR structure. So any kind of FIR structure can be constructed for HN or the filter that we require here for either decimator or interpolator. The new kind of structure which come into the picture for multirate processing, they are obtained by the polyphase decomposition. What is this polyphase decomposition? This is only rearrangement of the given equation. If this is my given equation, I can divide it into two sections, even values and odd values. From this odd value bracket, I can take Z inverse common so that all the inner values would have the same power of Z. This is going to give me the less complexity into the structure. So either I can represent the given equation in this format, or I can take the Z common from my first bracket here and generate another equation which is like this. So E naught plus Z inverse E1 or Z inverse R naught plus R1 Z inverse. So both are giving me same kind of structure with the difference of position of this Z inverse being in the beginning or end of the structure, giving me two type of polyphase decomposition, that is type 1 and type 2. So how do they look like? This is my type 1 polyphase structure in which this Z inverse is preceding these blocks of equation, and the second case the Z inverse would be after I have created these two structures, and these two structures would have the same powers of Z. So if one structure have been created here, this can be replicated n times as well. So these are n type filter bank which is creating using this polyphase technique. If I'm using it for the decimator, M would come here. If I'm using it for the interpolator, the L would come here. So in conjunction with all kind of FIR structures which are possible for multirate processing as well, we see that new two type of structures are possible when I talk about multirate processing, that is polyphase decomposition type 1 structure and polyphase decomposition type 2 structure. So in this way, we can implement various structures for multirate processor either for decimator or interpolator. So this is all for this session. In the next session, we are going to discuss about multi-stages of decimators and interpolator and how they are designed and implemented. So that's all for this session. Thank you.